Albert Einstein, a name synonymous with genius, physicists operated under the assumption that space and time were absolute and unchanging. This belief was rooted in the Newtonian framework, which had dominated scientific thought for centuries. According to this view, space was a vast, unchanging stage where events unfolded and time ticked away uniformly, independent of the observer. This Newtonian view, while practical for many everyday phenomena, crumbled when confronted with the behavior of light. Experiments with light, such as those involving prisms and wave patterns, revealed inconsistencies that couldn't be explained by classical physics. The speed of light, in particular, posed a significant challenge, as it appeared to remain constant regardless of the observer's motion. Einstein's genius lay in his willingness to question these long-held assumptions. Unlike many of his contemporaries, he was not content to accept the established norms. Instead, he delved deeply into the mysteries of light and motion, seeking answers that others had overlooked. His curiosity and determination set the stage for a revolutionary shift in our understanding of the universe. He boldly proposed that space and time were not rigid frameworks but rather flexible entities intertwined in a four-dimensional fabric he called spacetime. This concept was groundbreaking, suggesting that the very fabric of reality could bend and stretch. It implied that the presence of mass and energy could warp spacetime, altering the paths of objects and even the flow of time itself. This radical concept formed the bedrock of his theory of relativity. Einstein's equations, scribbled on chalkboards and in notebooks, captured the essence of this new understanding. They provided a mathematical framework that described how spacetime could be curved by mass and energy, leading to predictions that could be tested and verified. The theory of relativity, often divided into special and general relativity, challenged our fundamental understanding of the universe. Special relativity introduced the idea that the laws of physics are the same for all non-accelerating observers, and that the speed of light is constant in a vacuum. This had profound implications for our concepts of time and space, leading to the realization that they are interconnected and relative. Special relativity, published in 1905, dealt with the relationship between space and time in the absence of gravity. It introduced the famous equation E=mc², which revealed the equivalence of mass and energy. This equation not only revolutionized physics, but also had far-reaching implications for technology and our understanding of the universe. General Relativity, published in 1915, expanded on these ideas to incorporate gravity as a curvature in this space-time fabric. This theory provided a new way to understand gravity, not as a force acting at a distance, but as a result of the curvature of space-time caused by mass and energy. It explained phenomena such as the bending of light around massive objects and the precise orbits of planets. Einstein's theories, while revolutionary, were not without precedent. They built upon the work of earlier physicists who had laid the groundwork for these ideas. The scientific community of the time was vibrant and collaborative, with many minds contributing to the advancement of knowledge. They built upon the work of earlier physicists like James Clerk Maxwell, who had demonstrated the constant speed of light. Maxwell's equations of electromagnetism were crucial in shaping the understanding of light as an electromagnetic wave, and they hinted at the deeper connections between space, time, and energy. Einstein's unique contribution was to recognize the profound implications of this constant speed for our understanding of space and time. He saw that the constancy of the speed of light required a rethinking of the very nature of reality, leading to the realization that space and time are not absolute but relative and interconnected. This insight paved the way for a new era in physics, transforming our view of the cosmos and our place within it. Imagine a trampoline stretched taut. Picture its smooth, flat surface, ready to spring back any object that lands on it. This trampoline represents the fabric of space-time, a concept that is fundamental to our understanding of the universe. Just as the trampoline is a two-dimensional surface, space-time is a four-dimensional construct, combining the three dimensions of space with the dimension of time. Now, imagine placing a heavy bowling ball at the center of the trampoline. The weight of the ball creates a dip, a curvature in the fabric. This is analogous to how massive objects like stars and planets warp the fabric of space-time around them. This, according to Einstein, is how gravity works. His theory of general relativity proposed that gravity is not a force pulling objects together, but rather the result of objects moving along the curves in space-time created by mass. Massive objects like planets and stars warp the fabric of space-time around them. This warping is what we perceive as gravity. The more massive the object, the greater the curvature it creates. Just like smaller objects will roll towards the bowling ball on the trampoline, objects in space move towards massive objects due to the curvature they create in space-time. This is why planets orbit stars and moons orbit planets. This curvature dictates the paths of planets around stars and even the trajectory of light as it passes by massive objects. Light, which travels in a straight line, will bend when it passes near a massive object due to the curvature of space-time. Einstein's concept of space-time revolutionized our understanding of gravity. Before his theory, gravity was thought to be a mysterious force acting at a distance. Einstein showed that it is a natural consequence of the geometry of space-time. No longer was it an invisible force acting at a distance, but rather a manifestation of the geometry of space-time itself. This new understanding allowed scientists to explore the universe in ways that were previously unimaginable. This geometrical interpretation of gravity opened up new avenues of exploration in cosmology and astrophysics. Researchers began to study the effects of space-time curvature on the motion of celestial bodies and the structure of the universe. The interplay between matter and space-time is a fundamental principle of general relativity. Matter tells space-time how to curve, and space-time tells matter how to move. This relationship is at the heart of our understanding of the cosmos. Massive objects determine the shape of space-time, and in turn, the shape of space-time dictates how objects move within it. This dynamic interaction is what governs the motion of planets, stars, and galaxies. This elegant interplay governs the motion of celestial objects and shapes the large-scale structure of the universe. From the formation of galaxies to the bending of light around black holes, the fabric of reality is woven with the threads of space-time and gravity. As we continue to explore the cosmos, we uncover more about the intricate dance between matter and space-time. Black holes, for instance, are regions where the curvature of space-time becomes so extreme that not even light can escape. These cosmic phenomena challenge our understanding and push the boundaries of physics. With advanced telescopes and space observatories, scientists are able to observe the effects of space-time curvature on a grand scale. These observations help us to refine our theories and deepen our understanding of the universe. Computer simulations and theoretical models allow us to visualize and predict the behavior of space-time under various conditions. These tools are essential for testing our hypotheses and exploring scenarios that are beyond our current observational capabilities. Educational animations and interactive exhibits bring these complex concepts to life, making them accessible to people of all ages. By visualizing the fabric of reality, we can better appreciate the beauty and complexity of the universe we inhabit. As we gaze up at the night sky, we are reminded of the vastness of the cosmos and the intricate fabric that holds it all together. The fabric of reality is a testament to the wonders of the universe and the power of human curiosity and ingenuity. One of the most mind-bending consequences of Einstein's theories is the realization that the speed of light in a vacuum is the ultimate speed limit in the universe. This concept fundamentally reshapes our understanding of the cosmos and the very fabric of reality. The speed of light, often denoted by the symbol c, is not just a high-speed limit. It is a cosmic constant that underpins the laws of physics as we know them. Nothing, not even the fastest rocket or the tiniest particle, can travel faster than light. This limitation is not just a technological barrier, but a fundamental property of the universe. Even the most advanced propulsion systems or the most energetic particles in particle accelerators are bound by this ultimate speed limit. This cosmic speed limit is approximately 299,792,458 meters per second, often rounded to 300,000 kilometers per second. To put this into perspective, light can travel around the Earth 7.5 times in just 1 second. This staggering speed is a cornerstone of modern physics. This speed is constant, regardless of the speed of the source emitting the light or the observer measuring it. Whether the light is emitted from a stationary lamp or a speeding spaceship, its speed remains unchanged. This invariance is a key postulate of Einstein's theory of relativity. This constancy of the speed of light has profound implications for our understanding of time and space. It leads to the realization that time and space are intertwined in a four-dimensional continuum known as spacetime. This interconnectedness means that events that are simultaneous for one observer may not be for another. It means that time and space are not absolute, but rather relative to the observer's frame of reference. This relativity of time and space is a departure from the Newtonian view, where time and space were seen as fixed and unchanging. Instead, they are fluid and dynamic, shaped by the presence of mass and energy. This concept, known as time dilation, is one of the most intriguing consequences of special relativity. Time dilation means that time can stretch or contract depending on the relative motion of observers. This effect becomes significant at speeds approaching the speed of light. Imagine two clocks, one stationary and one moving at a significant fraction of the speed of light. To an observer at rest, the moving clock appears to tick more slowly than the stationary one. This is not an illusion but a real physical effect predicted by Einstein's equations. Special relativity predicts that time will pass slower for the moving clock relative to the stationary one. This prediction has been confirmed through numerous experiments, including those involving highly precise atomic clocks on fast-moving aircraft and satellites. This phenomenon, though seemingly bizarre, has been experimentally verified countless times. The implications of time dilation extend beyond theoretical physics. They are crucial for the operation of technologies like GPS, which must account for the effects of relativity to provide accurate positioning data. Thus, the unwavering pace of light continues to illuminate the path of scientific discovery, challenging our perceptions and expanding our horizons. Pause 3s. In this chapter, we will delve deeper into the implications of Einstein's theory of relativity on modern physics, exploring how it has influenced our understanding of the universe. We will also discuss the experimental evidence that supports the theory and its applications in technology today. Einstein's theory of relativity didn't just change our understanding of light and time, it revolutionized the entire field of physics. One of the most profound implications is the concept of spacetime, a four-dimensional continuum where time and space are interwoven. This framework has given us new tools to explore the cosmos and understand phenomena that were once beyond our reach. Consider black holes, for example. These mysterious objects were once theoretical constructs, but Einstein's equations provided the mathematical backbone to predict their existence. Today, thanks to advancements in technology and astronomical observations, we have captured the first ever image of a black hole, a testament to the power of relativity. Experimental evidence supporting Einstein's theories is abundant. One of the most famous experiments is the observation of gravitational waves. These ripples in space-time, first predicted by Einstein, were detected a century later, confirming yet another aspect of his groundbreaking work. The detection of these waves opened a new window to observe the universe, allowing scientists to study cosmic events like the collision of black holes and neutron stars. But the influence of relativity extends beyond the realm of theoretical physics. It has practical applications that touch our daily lives. Take GPS technology, for instance. The global positioning system relies on a network of satellites orbiting the Earth. These satellites need to account for both special and general relativity to provide accurate positioning data. If relativity were not considered, the system's calculations would quickly drift off, rendering GPS useless. In the medical field, technologies such as PET scans and MRI machines are rooted in principles derived from relativity and quantum mechanics. These imaging techniques have revolutionized diagnostics, allowing doctors to peer inside the human body with unprecedented clarity. Einstein's theories have also paved the way for advancements in particle physics. Facilities like the Large Hadron Collider, LHC, employ the principles of relativity to accelerate particles to near-light speeds, enabling scientists to probe the fundamental building blocks of matter. As we continue to explore the universe, the insights provided by Einstein's theory of relativity remain indispensable. They challenge us to rethink our perceptions of time, space, and reality itself. The journey of discovery is far from over. Each new experiment and observation brings us closer to understanding the intricate tapestry of the cosmos. Einstein once said, "Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution." His imagination has indeed given birth to a new era of scientific exploration, one that continues to push the boundaries of what we know and what we can achieve. Pause 3. As we look to the future, the legacy of Einstein's work will undoubtedly inspire generations of scientists to come. The theory of relativity is not just a scientific milestone, it is a testament to human curiosity, ingenuity, and the relentless pursuit of truth. Pause 3. Thank you for joining us on this journey through the mind of one of history's greatest geniuses. Until next time, keep questioning, keep exploring, and keep reaching for the stars. Pause 3. In this chapter, we will delve into the concept of the space-time fabric in greater detail, explaining how mass and energy can warp space-time. These ideas are central to understanding the profound implications of Einstein's theory of general relativity. Pause 1. Imagine space-time as a vast, flexible sheet like a trampoline. When you place a heavy object like a bowling ball in the center of the trampoline, it creates a dip or a curve around it. Smaller objects like marbles will roll towards this dip, drawn by the curvature created by the bowling ball. Pause 1. In a similar way, massive objects such as stars and planets create curves in the space-time fabric. This warping of space-time is what we perceive as gravity. When an object moves near a massive body, it follows the curved paths or geodesics in space-time. This concept fundamentally changed our understanding of gravitational forces. Pause 1. To illustrate this further, let's consider the Earth orbiting the Sun. According to Newtonian physics, the Earth is held in orbit by the gravitational pull of the Sun. But in Einstein's framework, the Earth is actually following a curved path in the warped space-time created by the Sun's mass. This curvature directs the Earth along its orbital path. Pause 1. Visual aids can help make these abstract concepts more tangible. Picture space-time as a grid. As a massive object like a planet moves through this grid, it distorts the grid lines, creating a visual representation of how space-time is warped. Pause 1. One of the most striking visual confirmations of space-time warping is the phenomenon of gravitational lensing. When light from a distant star passes near a massive object, such as a galaxy, the light's path is bent by the curvature of space-time around that object. This bending of light can create multiple images of the same star, a cosmic mirage that provides a powerful testament to the warping effects of mass and energy on space-time. Pause 1. Even time itself is affected by this warping. In regions of intense gravitational fields, time runs slower compared to areas with weaker gravitational fields. This effect, known as time dilation, has been confirmed by experiments involving precise atomic clocks. Clocks placed at different altitudes experiencing different gravitational strengths tick at slightly different rates. Pause 1. These insights into the nature of space-time have opened up new avenues of exploration in both cosmology and astrophysics. They challenge us to think beyond the confines of our everyday experiences and consider the universe in a profoundly different way. Pause 1. As we continue to probe the mysteries of the cosmos, the warping of space-time remains a cornerstone of our understanding. It is a testament to the elegance and depth of Einstein's vision, a vision that continues to inspire and illuminate our quest for knowledge. Pause 3. Thank you for joining us on this journey through the fabric of space-time. Keep questioning, keep exploring, and keep reaching for the stars. Until next time. Pause 3. In the final chapter, we will explore the speed of light in various mediums and its significance in the theory of relativity. We will also discuss the concept of time dilation and how it has been observed in experiments involving high-speed particles. Pause 1. The speed of light in a vacuum is one of the fundamental constants of nature, precisely measured at approximately 299,792 kilometers per second. This speed limit is not just a high-speed boundary, it's a cornerstone of Einstein's theory of relativity. Pause 1. When light travels through different mediums such as water or glass, it slows down. However, this reduction in speed does not affect the constancy of light's speed in a vacuum, which remains a universal constant. This constancy is crucial for the theory of relativity, as it provides a consistent framework for measuring space and time. Pause 1s. One of the most fascinating consequences of the speed of light is the phenomenon of time dilation. According to relativity, as an object approaches the speed of light, time for that object slows down relative to an observer at rest. This effect has been confirmed through various experiments involving high-speed particles. Pause 1s. For instance, particles known as muons, which are created in the upper atmosphere by cosmic rays, have a very short lifespan. When these muons travel toward Earth at nearly the speed of light, time dilation occurs, allowing them to reach the surface before decaying. This observation aligns perfectly with the predictions of relativity. Pause 1s. Time dilation has also been observed in particle accelerators, where particles are accelerated to speeds close to that of light. The internal clocks of these particles, so to speak, run slower compared to those of stationary observers. This experimental evidence reinforces the profound implications of relativity on our understanding of time and motion. Pause 1s. The interplay between the speed of light and time dilation challenges our everyday perceptions and compels us to rethink the nature of reality. It underscores the idea that time is not an absolute but a relative concept that varies with speed and gravitational influence. Pause 1s. As we conclude our journey through the realms of relativity, we are reminded of the transformative power of Einstein's insights. They have not only reshaped our understanding of the universe, but have also paved the way for technological advancements from GPS systems to particle physics. Pause 1s. The speed of light and time dilation are more than just theoretical constructs. They are windows into the deeper workings of the cosmos. They invite us to explore, to question, and to marvel at the intricate tapestry of space and time. Pause 3s. Thank you for joining us on this enlightening expedition through the world of relativity. Continue to seek knowledge, embrace curiosity, and never stop exploring the wonders of the universe. Until next time.